Okay.
So today we're gonna tear down the engine out of our 19 XRC car that was, you know, making some pretty good horsepower. This is a completely factory block, and I had debates about just blowing it up, seeing how much power it can handle. But a part of R&D is actually tearing it down before it's blown up and seeing where it's starting to have issues. So now there's like 600 miles, maybe 700 miles in this, hundreds of dyno poles. It's been to 36, or it's been to 40 pounds of boost, but all the testing that we've really been doing has been at like 35, 36 pounds of boost. It's been pretty much on E85 its whole life. The catch can was installed extremely quick, and you can see how clean these intake ports are. Now we don't have like the greatest light right now at the moment, but super clean. We have the XR42 turbo still on this. This thing here that you see hanging out, this is an exhaust back pressure probe. So we were monitoring that to figure out where the turbo was the happiest and when it's starting to kind of, you know, run out of steam, I guess, in the most simplest way to put it. So at all the boost pressures we test, we compare it against exhaust pressure to get like a ratio between boost and exhaust pressure. But other than that, this thing's never been taken apart. We're gonna take it apart on camera and talk about things that we see. I do know and expect to see wear in certain areas is based off the other engines I've been taking apart. But we have a sleeved engine, big head stud. We did some porting, did some valvetrain stuff. We're gonna keep a smallish camshaft in it. On the new engine, we're gonna be testing the, just literally dropping in the HO, the 900 HO intake cam. But for the purposes of this video, it's all gonna be tear down. So we're gonna get to it. I gotta drain the oil out of this thing. We just pulled it out, and we'll time lapse probably some of it, and then go into detail in some other areas. So. I guess we'll get the oil filter. Must have pulled the pin out of the front case. This does have a keyway cut in it. That's mainly to get the crank trigger in the correct spot. But based off what I can see here, our teeth are in good shape. I've seen the oil pump gear just grenaded, and these teeth seem to be okay. So get these bad boys removed. Where's my impact? Yeah. So this engine's dry sump, which is pretty freaking sweet. We got the sump pump, this sucks oil, and then the oil pump. So, and then all the paths in the bottom essentially allow this to do its job of pulling oil out of the system, and then there's paths in there that suck oil out of the oil pan on the back. So these things, they're just held on by like little snap clips. They're kind of a pain to pop off, but I normally don't remove them until the bottom is off because it's kind of hard to get a screwdriver or anything in behind it to pop it off. So you can ruin a set being a little too crazy with a screwdriver. So I think we got most of the oil out of this thing. We'll take the, probably should remove the turbo. You want to remove the turbo while I take the valve cover and stuff off? With a 12 and 13 mils. This is your cam angle sensor. There is a notch on the camshaft that sticks up, and this is what picks up on that camshaft. So if you throw a cam angle sensor code or whatnot, that's the cam angle sensor. Most of the cam codes I've seen are there's nothing wrong with the sensor. Actually, it's the engine's out of time, or you know, there's actually another mechanical issue.
Just bring it back from here.
That's sweet, I mean. It's like anti-seize. Gotta release the tension. There we go. Holy shit. Boy is in there. So it's a hydraulic tensioner with assist spring. The oil that's fed from the block into the cylinder head makes its way through this port, and there's a little oil hole, like check valve in this system. So as oil pressure builds up, it makes this thing expand and keep tension on the chain. Seen some issues with those, I'd say. Where they've blown apart. Yeah, and then slide this guide out. Seems okay. Chain out. Their system for camshafts is, I like it, it's pretty neat. If you happen to like ruin cam due to like lubrication problems, it's not like a whole new hit. Pretty interesting way of feeding oil to all this stuff, but these little seals, these are important. Must go back in. And it's a hydraulic bucket. I've been revving these to like 9,300 RPM. It's pretty high. Be interesting to see how these valve springs fared. But they're definitely solid. Yep, that's fine. So, something that we've been working on, it'll probably be released by the time this video is released, is we've essentially designed a solid bucket conversion. So, a sustained high RPM that these engines run with big boost and larger camshafts, even potentially on a stock camshaft, you have the possibility of this lifter pumping up and essentially hanging the valve open. Or you have the possibility of these pumping down and essentially causing more camera malfunction. So the hydraulic bucket, the downside to it, it's an extremely easy situation. It's self-adjusting, but when you're looking for maximum performance, the lifter can pump up too big if you don't have enough spring pressure and cause the valve to hang open. The other possibility is the lifter pumping down and then essentially lowering the lift of the camshaft and increasing the lash. So the performance way of doing it is solid bucket, and then you'd have to adjust lash, which we have two different ways we're going to come out with it. So we'll have a solid bucket conversion for essentially stock valve spring layout, and then we'll have a solid version for an aftermarket spring with an aftermarket retainer with a adjustment disc that we'll essentially put in there. So still got the stock head bolts in here. Can't even remember what the hell these are. 12s? Feels alright. Let's see if they're 11s. I think they're 12s. Yeah, they're 12s. Really interesting to see how screwed up these exhaust valves are from the aggressive two-step. That, you know that tool I have to remove valve springs? That, oh, yeah. Can you grab that for me? I'm only gonna take a quick look here for the video, but when you run two-steps or anti-lags that are aggressive with a lot of ignition retard, you're putting a ton of heat. The whole idea of all that is to put more heat in the exhaust, and the side effect is you make the exhaust valves get real hot. And these factory exhaust valves suck. Yeah. My buddy Jason bought this little tool. I don't even know where the hell you can find it. It didn't work for what we were originally going to use it for. Or something, I'm not sure. But it works really good for this. So it's got a little magnet in there, and you essentially just push, and then the magnet grabs the retainer locks. And then the cool thing is, you take this thing out. See, I've used this for freeze plugs and stuff. But when you flip it around, this is the installation side. It's pretty cool. So let's take a look at some exhaust valves. Where's my little thingy here? Steel retainer, nothing super special here. Big reason why you haven't seen many valve springs in the market for these things in the aftermarket is because the spring is tiny. Not a lot of room. So when we designed our valve spring kit, the whole idea was to actually fit a larger spring in the system. So we had to design the retainer to actually house the valve spring much higher up than originally planned, than originally designed for. So it requires a custom retainer to do it. And then it's a pretty common modern valve stem seal. It's like an umbrella style, so it also is the I guess you'd consider it like the spring seat as well to protect the head. Yeah, let's pop two of these out. I think I got a set of Ferrera exhaust valves in there. Can you find those for me? Doesn't seem too bad. Definitely a little lip there. But these, I don't know if you can see in much detail, but they have almost no margin, which is the distance from the end of the 45-degree cut, if that's what they run. The end of the cut, there's going to be a little flat section before it actually reaches the bottom of the valve. And on this thing, it's sharp. It's like a, it's insane how they design these exhaust valves for a turbo engine. But Ferrera noticed the problem right away, and they addressed it with a much better design. Let's take a look at this. Ferrera custom. Yeah. So, I'm sure you can see on this, you know, the dimensionally. Hold still. This way. Set them right here. That work? Sure. So the valve is actually a smidge longer than this valve, only because they've added margin. But the distance from where the valve actually sits on the seat, that's the same distance. So they fixed that with that margin. So this valve should last much longer and take the abuse of the aggressive, you know, fireballs coming out the exhaust. Here, put that one back. Thank you. So definitely some problems on interesting marks all the way out that far. That kind of looks like leakage. Be on the head side. Yeah, I mean that's I mean characteristic of, you know, possibly a little bit of leakage there. I mean, this thing has been abused. It kind of does the same thing though. It favors this side every time. That right there is completely normal. That one's a little bit. That one's a smidge.
Look at the coolant.
I mean,
I guess
so like, you know, the whole idea with, you know, converting to MLS head gaskets was having a really good, a really smooth surface. So you hear like some people talking about like RA, you know, roughness average across the surface. And these things, you know, they're not the greatest machine in the world. You could, I mean, you could just rub your finger on it and feel it. So as these expand at different rates, the cylinder head's likely to expand at a different rate because all the heat is being pushed into the cylinder head. And yeah, on this one, I mean, it's kind of odd that it's doing it more on the intake side. You'd normally have more heat on the exhaust side. This could just be, I mean, this could literally be a issue with coolant flow through the block into the cylinder head. So what I'm really getting to here is like the loss of material could just be the cylinder head and block rubbing on each other. So if you have a really, really smooth surface, they're allowed to move freely and not be grabby. But if you have a less than ideal RA, you start to see things like this where it starts to like scuff the, especially like the graphite or, you know, the sealant that they use. But it's odd to see it in the way that it's doing it on this engine. So, I mean, this thing's seen some power. We do have some aggressive two-step. It's odd to see it on the intake side. But, yeah, I mean, you do see a little bit here on the exhaust side, but absolutely no problems right here. So, interesting. Pistons are all there still, you know. Mm-hmm. Bonus. Some stuff that's kind of odd. The front bearing has almost no wear, which is like where the clutch is, and all the power from the engine, you know, gets loaded up right here, and generally this is where you'll see the most wear on the bearing. But there's almost no wear. This is generally dirt, is when you see these little, I mean, that could be from assembly, honestly, and you know, it just, they use a softer bearing in these for sure, and these like will, these bearings are designed to take in debris and get stuck inside the bearing and not, you know, forget about it essentially. But you do sacrifice the beating of the bearing if the crankshaft is beating against it. And on the very back side of it, on the stator side, is where we have the most wear. That could just be a tight clearance from Rotax, and with the horsepower, it beat the bearing out a little bit. Other things to look for is essentially like welding. So like there's a guy making a billet lower half because they think that the block is flexing, but you'll generally see it. You got your flashlight? I guess there's like such a small amount. That's a machining burr. There's a little bit right there. You can see the material will change, the surface will change color from them, you know, moving on each other.
Interesting.
Yeah. I don't see the block design being pinned right here is, you know, right next to, I guess, as close as you can get to the main journal. But I don't really see any signs of the issues that I would normally see when it comes to a girdle where that can't handle the forces that the engines are putting on it. I mean, I'm making, you know, I was making 300 something horsepower. But like on our high power Mitsubishi engines, we'll see the welding, the girdle actually shaking in the block from the horsepower, and the clutch, and you know, all that other stuff. This engine does get damped pretty well. You have a pretty heavy clutch assembly on it with a belt, and the belt kind of acts as a damper in the system. So from a strength and block integrity, this looks really good for how many poles I made on it at that power level. So the homeboys at Can-Am though put plenty of freaking RTV right here. Holy crap. Look at that. This is why you guys see RTV in your oil filters, because they go ham on the RTV process. That is an insane amount. Just need a thin layer. Well, anyway, we'll get the pistons out here real quick. The factory Can-Am rod design is pretty cool, where they cast oil squirters into them. I like that. Let's see here, about 8. No, 10. 9. It's a 9. It's a 9.
That's why you buy a 9 mil 12 point.
9. That's why I have only 12 points. Little freaking factory rods can take some RPM though. Way higher than. Let's do it this way. Let's get this one out first. Oh, that's mint. I mean, it's the non-crazy side, but this is a cracked rod cap. It's like super common in modern vehicles. They like forge the rod or cast the rod complete, and then they'll actually, generally they'll put like some imperfection right here and crack the cap off of it so that the two caps are in perfect alignment. It doesn't require a whole lot of machining to do it. Ringlings are in place. Really freaking nice. And look at that, it's pretty. Wow. Looks really kind of hard to see, probably in the camera, but I'm looking at the piston to wall mark that they leave on the piston. And these engines probably have a super tight piston to wall, but the shape is perfect. It's like it's supposed to be like a little football, right in the center.
Hold it there.
And it's perfect. It is so faint, you gotta like get it in the light to see it. But that looks really nice. Wear on the top. This is super common when you're making a lot of horsepower. It may be a little bit too tight on the clearance. If the oil can't sustain the hydrodynamic wedge is what you would consider it. So the bearing is not round, it's not perfectly round, it's egg shaped. So it's gonna be the tightest right here, and it's gonna be looser here. So as the crankshaft rotates around this journal, essentially it takes oil from a larger clearance and then squeezes it into a tighter clearance. If the oil can't maintain that hydrodynamic wedge, for whatever reason, you start to get touchdown. And we have a little bit of it here. So this could be, there's two ways to attack it. Better oil clearance, or more oil pressure. Put this one out. Let's put this one together. These things are so pretty. Be tang to tang. What the frick is going on?
One-time use.
You can actually see the tang, Joey, in a factory application. When they punched the tang into it, it was improper clearance, so it wore all the way down to the copper right there. It's pretty funny to see in OEM. Oh yeah, I didn't talk about the squirters. Yeah, so they cut these little grooves in there, right? So you got a bunch of oil pressure here, you know, so you got a thou clearance or a half thousandths of clearance, and the oil moves out, and then you would actually essentially have pressure on the side of the rod to the journal width. So if you run a tight journal width, then you can cut grooves in it, and then you can direct the oil in the locations that you want to direct it. So, I mean, we normally will machine them in a little bit of different manner than the factory rod, but in this instance, they're essentially squirting oil onto the piston wall. That's the design of it. We will normally put them on a straight angle up to squirt oil. And when the rod's like this, it's squirting oil on the wall, and there's one squirting oil onto the pin and under the piston. thing. Perfect. A little debris, sucked in a little bit of debris. Oh, that meant fly. That's funny. I mean, this is pretty much the end of the story, right? The rods and pistons seem straight, bearing seems okay. Same exact wear on this one. Right on the top.
Yeah. Might as well do the third one.
Word. Crankshaft. Crank's pretty nice. This is what we generally see in our Mitsubishi engines. A lot of the European engines, I guess, they have a rolled fillet. So they have a machine that comes in and pretty much forces this material into shape to add a lot of strength. A lot of aftermarket companies will generally just do a straight machined fillet instead of that press fillet. But that adds a ton of strength to this right here. I mean, it's a pretty... Crankshaft seems to be pretty sweet. We might break them one day, but that will happen in time. The engine has squirters. These are fed directly from the main galley, main oil galley. There's a little pressure. They kind of have like a internal spring ball assembly. So if oil pressure is really low, they won't be squirting to essentially, like, you know, prevent oil from getting to places that are more important. But when engine oil pressure gets up to a point, then we'll start squirting oil onto the bottom of the piston to help cool it. These are, I mean, in the type of driving we do, in the environments that we drive in, I'd say they're pretty important. Kind of required in turbo applications with this style piston. But that is kind of like a, you know, basic rundown of what we look for, or what people generally look for while tearing down an engine. You know, this thing might take a couple main bearings. Its pistons seem really good. I mean, if you were to just tear this down for whatever reason, you know, there's more measuring that has to be done, but it'd be a pretty simple re-ring, couple bearings, some new hardware, and put it back together. But this engine right here is seen 9,300 RPM, almost 40 pounds of boost, like I said earlier, and it seems to be in pretty good shape. So we're dropping our built engine into this car. We're going to turn it up even more, and it's kind of customary for us to tear them down every year just to take a look at everything. So we'll probably do another video on our built block when we get to that point. Until then, it's John at Whalen Speed R&D, right?
Indeed.